Hello, everyone. My name is Mehul Motani. I'd like to welcome you to the last talk for the first half of 2021 of the seminar series, Information Theory in Singapore. Well, if you're here for the first time, welcome to Singapore. Well, virtual Singapore. I wish we could greet you in person, but these are strange times and things are getting better, but for now, this will have to do. Behind me is a picture of the Singapore skyline and Marina Bay for you to enjoy. So I hope this pandemic passes soon and everybody gets vaccinated and you can all visit Singapore and see our beautiful country for yourself. The Information Theory in Singapore seminar is organized by a team that includes Han Mao from NTU, Tai Kwei and Tang from SUTD, and me from NUS. Our aim is to promote, advocate, and spread the joy of information theory and coding theory within Singapore and around the world. As I said, this is the last talk in the first half of 2021. We are planning to continue and you'll hear more from us at a later date. Please do register so we have your email in our database. Okay, before we get going, let me address a few logistical matters. Please keep your microphone and video muted for the duration of the talk. If you have questions, you can post them into the group chat and we'll address questions in the Q&A at the end of the talk. Now, it is my great pleasure to introduce Professor Negar Kiyavash as our speaker today. Professor Kiyavash is a faculty member at EPFL, Ecole Polytechnique Fédérale de Lausanne. At EPFL, she is with the College of Management of Technology and holds the chair of business analytics. Prior to EPFL, she was a faculty member at the University of Illinois at Urbana-Champaign and at the Georgia Institute of Technology. Her research broadly sits at the interface of social science, business management, and data science. And specifically, her research focuses on topics like data analysis, data security, discrete optimization, and causal inference. Outside of academia, actually, there's a lot of things I could say, but I'll just leave it at something I learned about her recently. She's an avid reader of fiction, and I think she likes Russian and French literature. Is that right?
Yes,
Negar?
very much so. Yes.
Okay. Now I'm honored. Now I'm honored to have my colleague and friend Negar Kiyavash share her thoughts with us today on database alignment, fundamental limits, and efficient algorithms. Let us warmly welcome Professor Kiyavash.
Thank you so much, Mehul. As always, you're very kind to me. So I hope the talk is okay. It's, I haven't done many of these Zoom talks. I'm getting a little bit better at it. So I hope this would be okay for the students. So I don't know, what is the protocol? Would you like to interrupt me, maybe speak up, or you rather keep the questions for the end? Whatever you prefer is okay with me, whatever is the protocol.
Okay, right now we'll just have students and the audience members just type it into the chat, and yeah, and then so as not to interrupt your flow, we'll take them at the end.
Okay, perfect.
Is that fine?
Thank you so much.
Okay.
Yeah, that's perfect. And this is the first time I'm giving this talk, so all the slides are basically were tweaked up to last night. So I thought it would be nice to give something different, and so my apologies if it's not completely perfect, because as you give a talk a few times, it improves, but I hope it's okay. So I'm gonna talk about these fundamental limits and also some algorithms for this problem of database alignment. So let's go here. So why am I actually interested in this problem, right? So first of all, as we would discuss in a few examples, this is actually related to certain incidents of privacy breaches, and it allows us to understand by discussing these examples why this problem is actually of interest to us. More importantly, it actually has a very nice mathematical structure, and we would see that it is also very related to some of the problems in information theory fundamentally that we have been excited about. And I would discuss in this talk two setups. One of them would be for the case of finite alphabet, one would be for the Gaussian case. And I would give you first that what are like some intuitions and results we get in this problem. And then depending on the time, I hope that I can tell you a little bit about how the analysis is done, at least for two cases. One is in this so-called high correlation analysis. And then I would talk about also the low correlation for a specific type of alignment. So as we all know, of course, you know, there is a lot of data around us, so is also data collection. So more and more companies, as we interact online, not only they give us services, but they actually end up by us, virtue of us using their services, also collecting information. So this is really nice because as we have these very many sources of data, actually this allows us to pool this data together, and this, you know, might help us to be able to do things that we were not able to do before. And you know, often people have still concerns though, right? So when you use various applications, you enjoy the benefits it provides you, but you want to have at least some level of data protection. So most of these providers have some version of actually anonymization, which is employed in their data collection, right? But what is interesting is that the data intrinsically of a user has natural correlations embedded in it. And this is nice in a sense because you have these various data that pertain to the same user. It can allow you to, through this like alignment of the information, if you're doing it cleverly, actually do inferences or do processing that was not possible to you before, right? So this is actually quite nice and allows you in some sense to do more than what you could do. On the other hand, on the flip side, you can see that again, having the same data, this correlated data in many different ways, even if it's anonymized, you could possibly think that, okay, these correlations can create a situation that it would breach the privacy. So, I mean, we see these things all the time. I mean, on various media, like, you know, so you can, like, you know, for instance, one of them was that it was a huge breach that happened in 2010, that Netflix actually canceled a contest it has, which was, the reason was that there were all these lawsuits they got because of breach of identity of folks in the database that happened. And this problem is exactly of the type I would like to discuss now. There have been, of course, many other breaches, but let's make sure that, you know, like we understand what is really the issue here. So we really want to, like, you know, understand this trade-off, right, between the usefulness of the data, which is the fact that allow us to like pool this data, but also we want to make sure that, you know, the same features, right, that are useful in terms of our inferences are not also creating possibly breaches on the privacy. So, you know, there's been, again, there was this huge concerns also about the privacy of the users in census data and so on. So the issue is this, right? So what we are really concerned is that if information pertaining to, let's say, a user is collected, then you might have concerns that this information fundamentally allows you to, even though you're using the aggregate, could possibly say something about a specific user. So this has been a concern in this so-called area of differential privacy. And to understand what goes on in the differential privacy, I want to briefly describe what does this mean. And what we are discussing in this talk is not differential privacy. So I want to have this early on. So I always, you know, get these type of questions that people ask me, is it same as differential privacy? And I just want to preempt that. So it is not what I want to talk about today. So let's make sure what is differential privacy, right? So we would have actually two databases that are identical, except that there is one user information is removed. So let's say D1 is your overall database, D2 is the same database, except that you actually remove a certain person's information. Then you can think about some algorithm which is actually doing inference here, right? So this output of the algorithm would be what is publicly reported information. And what we want to make sure is that you cannot actually estimate whether or not a certain person's information was included in data based on what is reported, right? So you're basically considering this like, these two probabilities. So one of them is that, you look at the report of this algorithm, right, when it works on the data set one that includes this specific user, and then compare it to also the case that you kick out that specific user. What you want is that these probabilities would be not distinguishable, right, enough, so you cannot actually decide whether the user's information was used or not in whatever inference that was done or whatever public data was published. So this is basically what differential privacy does, right? So it is very different than the problem I want to discuss now, because here actually you're concerned about whether a specific user's information is present. What I'm concerned about here is actually the fact that there would be information that is going to pertain to multiple data sources, right? So what we are concerned here is that what is leaked through this aggregated form, right? When you actually can pool bunch of data sets, what can you learn about these users? So let me describe this alignment problem. So what do I mean by that more formally? So this is the scenario that I'm interested in. Let's say I have some data structure pertaining to some users, and I have another data structure. Let's call them data structure 1 and 2. And these colors are discussing the identity of a user. So I'm trying to encode the identity of the user. So as you see in these two data sets, there are two users that are shared between the data structures. So one of them is in the first data set, you have the blue user and the green one. In the second one, you also have them. But of course, there are other people present in these data sets as well, right? So as you see that these users in these two sets actually have some data that is pertaining to them. So the way it happens is that you obfuscate these things, right? So you want to anonymize them so you don't know who is the person. So everyone looks gray, right? So you cannot actually see that these are now the same people. The blue people's information is across these two data sets. The problem is this: often there is some features there, and these features are correlated, right? So the question is that can you use somehow the correlation in the structure and figure out these are the same people? Why is this problematic? So I mean, on the positive side, you can possibly think that, okay, you can use this anonymized data set and then do inferences jointly, because now you figure out these pertain to the same user. On the flip side, let's say one of these users, one of these data sets, as a user, you consent to it publishing some information while you did not feel comfortable having the information in the data set, let's say one, to be public about the user. If you can actually realize that these are the same users, then you end up de-anonymizing information about a set that you're more sensitive about, right? So that is really the problem. Let's think about an example. Of course, one would be things like medical reports, right? Would be an issue in a database, right? So if you can somehow figure out by this alignment that in a database that you're discussing medical records of a person, this is of course sensitive data, you might not want it. Sometimes there are also situations that these data sets have some notion of this bipartite alignment, right? So this would be what I would discuss in a second in more detail. Let's say you're rating movies, and if you can through some other structure figure out that these users' identities, who they are, then you can learn something about what movies I'm watching, and I might have interest of not revealing that, for instance, right? So you could also have another setting, which would be that these users' information, which is anonymized, is not by just single features of these users or multiple features, it's through their interaction. So this would correspond to a setting that is so-called basically this graph alignment problem, which is also a problem I have worked on, but it would not be focus of this talk, right? So for instance, you can use people's connections to learn who is their to learn their identity, right? So you could of course also have combinations of any of these settings that can happen in your data sets, right? So let me tell a little bit about this Netflix disaster, what happened, right? So it's related to the so-called bipartite alignment of movie ratings. So this is what happens. So there was this Netflix prize data set, and the data set had these features. So you had some user IDs. Then, as you can see, these user IDs are the basically the circles on the left. And the users were watching certain movies. So the movies are the squares on the right. And when you have connection, it means a user had rated a certain movie, right? So you had this idea of the movies, you had the users, and then you had ratings of these users for various movies, right? So you have this bipartite structure. Then there is another database, this IMDB, where again in this database you can have some information. Here is very similar, except that things are not anonymized anymore. So hence I have color now. So you have these users like various, either they could be just individuals or they could be experts for movies. So they again have access to these movies, and then they publish ratings of certain movies. So what ended up happening, right, so is that because in IMDb users tend to register with full name, then they might avoid publicly rating certain movies, right, of their interest, because it gives some information about them that they might not want to reveal, right? So you can imagine that the movies you watch, for instance, can say something about your political views, your religious beliefs, or even your sexual orientation, right? These are things that you might not want to publicly disclose. So what was possible is that by this paper by Narayan and Shmatikov, they showed in 2006 that you can actually break this anonymity of the Netflix prize data set. And the way they do it is by this virtue of this matching of the IMDb profile of the registered users with, because they're saying which movies they're liking, and then you look at these correlations of their ratings and what movies are in there. Of course, it's not exactly the same data set, because as I told you, you might in the Netflix have watched other things because it's anonymized, but still you can use these correlations between these two data sets and learn the identity of the raters. So this was a huge problem, and it ended up like starting like slew of lawsuits, and eventually Netflix ended up pulling off their basically challenge, and this was exactly because of this concern, right? So had to cancel this competition. So we know that there is a problem here, but mathematically, how does one capture this? What can we say about it? And this was what we were excited about and decided to take a look at it, right? So let's try to at least look at one version of this kind of alignment problem, specifically for databases today. And this is where I want to describe the mathematics of it, right? So you have a database. So in general, it's some unordered set of features, right? Which is each is associated with a user. So these black line are the set of features, and those dots that I have are the users, right? It's there. When I put color is to specify that they have a specific identity, right? So this could be some database, and you can have another database where again, you have users. This time I'm showing these users with the squares here in this database, right? And then they could again have some features in the other database. So when I have the same color, this is to basically specify these are the same users across the two databases. And of course, they have various features or data pertaining to them. So I would make an assumption in this problem that all the features in a single data set are independent and identically distributed. This is to make life easier for me for the analysis. Still, it remains very challenging. So it means that various users' data is independent of each other, but we also assume that they're identically distributed. But across databases for the same users, of course, we have to have correlation, right? Otherwise, there's no way of matching them. So you have this joint distribution of the same user across these databases, right? So that is where the correlation exists. So as I mentioned, you would have it across all of these, but, so the features associated with each user are jointly distributed, but each pair is IID, right? So again, the red pair and the blue pair are IID. So if you look at their joints. So, so this would be basically the structure that we are interested in and we are studying, this database model that I'm considering. So I'm gonna use U and V, cal U and V, to denote the set of user identifiers. This is identity of the users in one of the databases, and the other one, you know, I'm just gonna discuss two databases. And let's say there is some mapping. So this mapping M is what one likes to study. It basically tells you, you know, which user identity is corresponding to another user identity across these databases. So this matching of these basically identities is called M, this mapping that's, you know, among the identifiers. And as you can imagine, this is what's going to happen, right? So I'm going to use this notation, this W of M. These are the pair of users that are mapped across databases. So in this example, it's the red pair and the blue pair. And then you have this U of M, which denotes the set of users that through this mapping M got mapped to someone in database A. And V of M are the set of users from database B that got mapped to someone in database A, right? So this basically denotes, because I would need this notation. Is the notation clear? If you at this point is not clear, I'd like to just see, I don't know if I see the chat. Make sure that this is okay. So this is okay. So I just want to make sure that notation is clear. Okay, perfect. Because I don't want to lose you, and then at the end of the talk, you know, you basically could not follow the notation. Thanks a lot. So then basically, I have some arbitrary features for the data sets. Let's call the ones for data set A. I'm going to call them X. I use the symbol X to denote it. For the features in database B, I use Y. So in general, of course, these are vectors, right? So they don't have to be a scalar. So this could be a vector of features. You know, it depends on the dimension of your feature, right? So then I can talk about now these marginals, right? So depending on, of course, your alphabet is discrete or not. So you have PDFs or PMFs of these features that are marginals for each data set. And you have this notion of the joint, right? So this joint is for a pair of users. And recall that I describe pairing of the users via this map M, right? Hence, you talk about this FXY induced by M, right? So condition on what was the pairing. You have these joint features. And then we assume that all these distributions are known in our problem. Of course, you know, learning them would be also an interesting, you know, harder version of the problem. So then what we have is we can naturally define the log likelihood, and the likelihood is of this form, right? So for all the pairs that are mapped through this matching, so these are UVs that are in this WM. So recall that WM was set of users that were matched by this matching. So I have this joint likelihood, which is this log of XY. And then for any users that were not matched either in set U, so then I have this basically U's in U set minus UM. So these are the guys that through the matching M were not matched. So for those, you just have a marginal, right? So you have this F of X, and similarly, you have the corresponding marginal for the users in the other data set B, which I denote them by these V's, right? So this would be your log likelihood, right? So what I can do is I can rewrite its likelihood, and the way I do it is that, you know, I'm just playing with you know, I'm just adding and subtracting these marginals. And if you do that, then you know, your life gets slightly easier. Is that you basically would be able to remove this set minus thing, and then consider all the users, and then you get the red terms, right? What is in the denominator that you would have there. By the way, there is a typo here. This should have been F of Y, because in user, for the users in the data set B, I use Y. So my apologies here, but I think it's clear. So then what is nice is now I can realize that, okay, the last two terms don't depend on M, so I can just get rid of them, right? So when I talk about the likelihood, I just need to consider the first basically term that I'm using. So now let's think about what is this basically quantity that we are considering, and I'm sorry, all of these should be f of y when you have b there. So you're looking at this so-called information density matrix. So what do I mean? For each pair of users, so as you can see, this is if these values are in R, then you would have a matrix of dimension u times v. So this is the size of these two databases. And then at each entry of them, you would have just this value, which is basically this information density value. That is it is this log of the joint over the marginals, right? So I can also have another matrix M, which is encoding my mapping, right? So it's just the indicator. So whenever a mapping M was mapping some user U and V, I'm gonna put a 1 there at that position, right? So basically M is gonna map this user's U and V. There is 1 there, otherwise you have a 0 there. So it's a matrix of the same dimension again as G. So then when you discuss this summation that we discussed, right, for the likelihood estimator, I can just write it in this notation, which would be basically this inner product between the matrices. It's just to make my life easier, and I can just carry this. So remember that this is just encoding basically this information density and of the likelihood versus also what pairs of users were matched through this matching, right? So clearly this G is a function of these basically databases, and it's something I can compute, right? Because remember, what is its form? I have access to all the distributions, as I told you, so I can actually calculate these densities, right, and fill up the matrix G. So M is a so-called partial permutation matrix. The reason it's partial is because you might not actually map some users, right? And this U and V in general don't even have to have the same dimension, right? So hence you call this a partial permutation. In certain cases, it could be also exact permutation, right? So if you know M, then what, like, so if you knew the matching, like, what is the correspondence of users across these data sets, then maximizing this product GM would be equivalent to this so-called linear assignment problem. So it's a problem that has been well studied in the literature, and you can actually use this so-called Hungarian algorithm, and you would have a nice polynomial time algorithm that actually can solve this. Why is this interesting? First of all, you want to say that this is a problem that it's in terms of its complexity, it's in its polynomial time, and it's different than the case of, say, graph alignment that some of you might have heard of, where there is no such polynomial time algorithm. So these are problems that are very nasty, and lots of work has gone into understanding, can you have any efficient algorithms or in what regimes, right? So this database alignment has a polynomial time algorithm. So, however, when you are doing this MLE, you in general don't have this M, right? So I don't know all my, I don't know the mapping. Your goal is to learn the mapping, right? So if you want to find this complete mapping, this actually could be still very costly, right? So there are other algorithms than you can imagine that I want to briefly discuss. That is, like, if you don't want to do complete MLE, it's too costly, and it makes sense in certain application, you might want to use other algorithms. One of them would be the so-called, for instance, maximum row alignment. So what does it do? So if you have a user in database A, you just want to, find a corresponding user in database B, and the way you do it is through the features, right? So what it means is that you ignore all the other features in A, and you just pick features in B that, maximizing this likelihood, right? So it's equivalent to actually picking the max entry in a row of your matrix G, right? So you basically don't care about the entire matching. You're just, considering this a specific user, right? So that's one way of doing it. Another way, like if you're doing just, another cheap algorithm would be this so-called thresholding, which is that, all you do here is you want to discuss that you agree that two users are possibly the same people, and the way you decided if it's their feature pair is correlated enough, right? So in this case, you just perform likelihood ratio tests with some threshold, right? That's basically if as long as, you know, the corresponding entries in these two matrices, in these two data sets that you're looking at in G are above a threshold, then you're gonna say, okay, so it's possible that this is the same user, right? So this is the so-called thresholding rule. So all of these estimators actually have a linear programming formulation, right? So let's just once, and you see that the relaxations of each other, they're nested, right? So let's for now assume that, you know, without loss of generality, that, you know, that my U database is smaller than cardinality of database A is smaller than database B size of the users. Then if I'm writing this maximum likelihood estimation, so if I want to maximize this inner product between G and M, and you notice here that I'm using now lowercase m because it's a specific mapping, right? So I'm considering it for a specific mapping, right? So then if this is basically the maximum likelihood is this estimation, so you're maximizing this inner product, and then you want to make sure that, you know, you have valid matchings, right? So what I mean by that is that, you know, you want to make sure that if you basically you know, considering a certain user, so across both rows and columns, you have these properties that you pick up just a single correspondence, right? And these are the basically the inequality and the equality conditions here. And of course, these are mappings between them. So these m's, recall that it was in 0, 1. So I always have this also condition that, you know, my m cannot be negative, right? So this is the linear program. Now, if I wanted to do this maximum row estimation, I don't need to enforce anymore that I have like just this kind of pseudo matching. So I can relax the initial inequality. And then all I care about is that, you know, for a row, I'm gonna in that row pick up the best corresponding, like, you know, V in the other database, right? So as you see, I have relaxed one of my conditions from the original LP to get this one. I can also just shift this matrix G by some amount tau, and it really doesn't matter. It doesn't change my maximization because I have this equality constraint, right? That the sum of the m's have to be 1. So it doesn't matter if I was like, you know, shifting it by some constant tau. Why do I care about it? Because if I'm thresholding, which was what I was discussing to you, then the LP I would solve would be this. So you have some threshold that is acceptable to you. So you as long as you're above a certain threshold tau, so then you can actually solve this other LP. So as you see, this LP is in further relaxation of the maximum row, right? So it basically here, because I'm gonna now relax this summing of the m's being equal to 1, I need to put an upper bound, right? Otherwise, you know, there it was basically forcing me not to pick up some unbounded m. So I need to now put an upper bound, hence the blue line on the bottom, to make sure that, you know, this is basically well regularized, this MP. So this would be the nested chain of these basically various algorithms that I can actually talk about. So if we have these type of algorithms, let's see what we can learn. So what we learn is this. So I first tell you a little bit about what are the results we have, then I would describe, as you know, as time permits, at least how we get some of them. So if you have a finite alphabet setting, so all the things in this database A and B are from some finite alphabet, then it so happens that there is some critical information theoretical measure is going to pop up in a second. I'll show it to you. And then this allows us to drive basically achievability and converses. So let's assume, you know, just to make life again easier here, that the size of the databases are exactly the same and they're equal to n. And then if the size of the databases are the same and equal to n, then we get this achievability, which tells us this information theoretic measure that we have, as long as it exceeds a certain amount, and this amount is dependent on size of your database, right? Then the maximum likelihood always finds the correct mapping, right, with very high probability. If, however, this threshold is tight, as you see in some sense, right? So if this information theoretic value is less than this critical 2 log n amount, then the algorithm does not actually do well, and, you know, it pretty much fails, right? So it can only find the correct mapping with this small probability O of 1. So when the set of the basically the alphabet set is finite, and then we have the same says databases, right? So it's the smallest number of the errors, right, that are going to be dominant, right? So it's basically if one user is mapped to so you would basically have this size 2 errors always, because remember that if I'm mapping a user U1 to some V1, and then you make a mistake, it's the wrong pair, it means that there's another pair you have messed up too, right? So you always at least have these errors of size 2, right, that are happening here, which is basically, this is what I'm trying to say here. So if I have 2 mappings, then they, you know, they differ only with a pair, it would be impossible. So they should at least differ in 2 pairs, right? Because you always mess up at least 2 pairs when you're doing it, right? So then if you're in a setting that this, let's say M is the true mapping, it's the correct one, and you make a mistake whenever you're in a setting that the wrong mapping M prime ends up giving you a higher likelihood, right? And then the value of the likelihood of be exactly of this form given the description of the matrix I have for you. So this is the error event that you would have. So recall that I had this joint, and finally here I have written it f of y, so it's correct on the denominator. So I have this g, which is basically my density. And then I have these variables, right? So x and y, which was denoting my features. And I told you the error event here that you're interested in is that the wrong mapping ends up giving you a higher, basically, a higher inner product, right? So it looks like the, you know, that M prime was the true mapping while it's a mistake, right? And to analyze this error event, what we end up doing is just we apply a Chernoff bound in this setting, and then, you know, this is just from the definition of this G, the entries of the matrix, this basically becomes calculating this expectation. And again here, like, you know, when you take this expectation, recall what was the form of our joint. So you basically just multiply it by the joint, which is of the form of the denominator, right? So it's just that the denominators has this square root, so it gets canceled out and you end up getting this quantity. And because it's an expectation, of course, I'm summing up over all these pairs, right? So this would be the form of this error probability. So now what we end up having is this quantity, and I can actually write this quantity as a trace of some matrix, and this matrix is basically of this form that each of the entries is just this square root of the joint of this x and y. So why am I doing all this work? Because what I want to now show to you is that this quantity I can call, so earlier on when I was describing my results for you, I wrote it in terms of this kind of magical quantity, that there is this information theoretic quantity, this notion of information of us capturing by this circular information. And it is of this form, right? And if you just once again look at the analysis, then it's clear where this comes from, right? So I didn't want to just write for you that this I equals this log of this trace of these matrices. It's basically, you can just see that it pops up naturally from a simple calculation of the probability and then using the Chernoff bound. So this basically quantity is what captures you know, it's the relevant measure of information in this database alignment problem that actually captures you know, what is the amount of correlation that you need to either be in the achievable case or be in the impossible setting, which is the converse, right? So this basically tells us that, you know, as long as this correlation captured by this I circular is higher than a certain threshold, then, you know, you can actually find the right matching, otherwise you fail. So it's very similar to many of the other classic information theoretic problems that we have seen, right, in terms of, so let's say channel coding and so on, that you have this quantity that basically has this phase transition based on, like, you know, if it's larger or smaller than a certain boundary or threshold. So in case that your databases are not from a finite alphabet, but rather they are from so-called Gaussian, then we could again analyze this, and the analysis here becomes more familiar in terms of the quantity that we see. So here the information theoretic quantity that captures the correlation is just the mutual information. And again, if we assume that, just to make life easier to describe the results, if assume that the size of the databases is the same as is n, then I get again this achievability and converses, which look very similar, except that here you use basically mutual information is the quantity that tells you that when are you in each of these settings. So in these results, what I described for you, you consider a success if you were getting exact mapping, right? That was my definition of my basically achievability. But sometimes you actually might not be interested in finding exactly the mapping, but you're more interested in this error exponents, right? So you want to know what ratio of the errors, what ratio of users you are erroneously matching, right? And ideally, you're interested in the cases, of course, that these are vanishing, right? So as I said that, in the top part, what is in the slide, it's the result I described to you, is this so-called exact alignment, but we could also have an almost exact alignment. And if you notice, there is a factor of 2 difference between them. So if you look at the threshold of the achievability and converse here, instead of being this 2 log n, now it's log n. So if you have less correlation, you can still recover, like, most of them matching, right? And then as you see here is that, the amount of the mistakes you make are in basically in expectation in the achievability is O of n. And then in the converse, it's basically omega of n, right? So you see that there is a basically difference here, but you still have this vanishing errors that you are recovering. So to show it, it might be nicer to look at a graph. I think it's easier because, I don't have exact description, so you have basically the growth rate of your errors, but we don't have the exact function. So I think it's easier to maybe have some graphs to give some intuition what is happening here. So in all of the graphs I'm going to show you from now on, I'm going to have this x-axis, which is basically in terms of the mutual information. I'm just normalizing it, is that instead of plotting mutual information to make my life easy, I'm dividing it by this log n term, right? So I'm basically describing this x, right? Because I have this I equals x log n. So my x-axis is just this quantity x. And on the y-axis, I'm basically showing the error, right? So let's say the expected number of your errors in terms of this n is some n to the y. And what I'm plotting is just this y, right? So it's the error exponent that I'm plotting for the Gaussian alignment. So what is my converse saying? So if you recall that in this higher correlation setting, when, I basically was interested in getting the perfect alignment, right? So as long as my, so this was the converse that I had. So remember that I'm just dividing by these log n's to work with x's, make my life easier. So as long as my x is less than 2, then what I would have is that, my exponent, this y is always larger than 0. So it means the red region is not something that I can achieve, right? So basically this is the region where x is less than 2, and then y would be less than 0, right? So I cannot have such a exponent. That would not be achievable to me. That's what the converse means. So for the low correlation case, right, where I was interested in basically seeing that, okay, what if I change this value of the threshold instead of 2 log n to this log n, then if you recall, then the form of my converse is what is written on the first line. So this means that now my basically region that is not attainable to me is this other red region. So here's like a darker red region, which is basically if you would have this setting that, if x is less than, so sorry, I think there is an error here. It should be if x is less than 1, my apology. So if x is less than 1, so I don't have enough power, then you basically have that your y is always gonna be larger than 1, right? So this would be what you would basically would be impossible to you in this setting. So this would be the two converse regions, right? What is not attainable to you. So let's look at the achievability. So if you're looking at the achievability of the MLE, again, let's remember in the case that I have this high correlation, so I had the factor 2, then if we look at it, we would see that, you know, if in this case, x is larger than 2, so it means your basically mutual information was larger than 2 log n, then what you end up having is this line, right? So y has to be less than this 2 minus x. So this is the region, the green region is the exponents that are all achievable to you, right? You can do any of these. Now, if we have low correlation, I end up learning something else, which is that, you know, in this case, remember that your basically mutual information was larger than log of n. So I get this x larger than 1, which is what is depicted also here. You get this circle, like, you know, this quarter circle, which is depicted in the picture. And this would be basically the region you can get from analyzing this low correlation, right? So this is what MLE allows you to learn. Interestingly enough, if you were doing the max row alignment, which is what I told you, when you actually relax this requirement of the entire matching, you were just doing it across a row, then you end up getting this other setting, which is depicted here. So you would basically have one, which is a line, a segment. So this blue curve, if you look at it, like, you know, at some point the curve is for the low correlation, it's not a line anymore, but then, you know, above a certain value it actually becomes a line, right, for the x. And you know, the regions for the x are basically depicted here. So when you have low correlation, you have this achievable thing which is above this basically blue line, right, the blue curve, right, which at some point is a straight line, above that is not a straight line, depending on where you are. Similarly, for the thresholding, I can also get this, and you would get this other basically line, which tells you what is actually, what kind of exponents are achievable to you. So I think it's easier to look at the curve and understand this, you know, than just maybe the statement of the theorems. So I have a little bit of a time. I want to use it to just give you a little bit of how does the analysis work. So it gives some intuition. I think it would be helpful to look at it. So I'm going to use this basically graphical representation of my matching, and then recall that there's a corresponding matrix M, right? So what do I mean by that? So let's say if my true matching was matching user 1, U1 to V1, and then U2 to V2, and so on. Then if I was writing this matrix M, as I told you, it was just the indicator matrix. So I had zeros everywhere except ones for the correct pair, right? So you would get basically this setting. And in general, these matchings don't have to be of the same size, right? So there's no reason for it to be of the same size. So you can use this V prime to indicate all the other guys in the second database that I didn't match them, right? So let's consider another matching, and let's say this is M prime, and this matching would pair up different users. So we usually use notation M for the true matching, and then M prime is the erroneous match, right? So this erroneous matching, the M prime, would do some of them correctly, as you see, like it's getting user 1 correctly, maps it to V1, but for users 2 and 3, it actually swaps them. And as you see, between users 4 and 5, you know, he maps user 4 to user 5, but for user 5, actually, it goes to somebody else, right? So some other V prime, which was not part of this actually correct set. And the corresponding M prime is, of course, this, right? Again, I'm just putting ones wherever users are matched, right? It's just description of this M prime. So now, clearly, I can look at difference of these two matchings, right? And what happens is that wherever you got it right, you're going to get a 0 on the diagonal. Because user 1 was correctly matched, I have a 0 on the 1-1 entry. But if you, for instance, look at the 2-3, you have this basically mistakes, right? So you get this -1 and then the +1s there that are coming from the mismatch of the alignment. Similarly, it's happening for the 4 and the 5th guy, right? So you get these basically mistakes. So what do I mean here? So what do we learn here is that you get these components, right? So every time you have these like matchings, like it ends up corresponding to some blocks in this matrix M. And specifically, you know, every time I look at the difference of these two matchings, I can imagine that it's going to induce multiple blocks, right, that are present here. So it's important to realize that if there's a matching M1 prime and M2 prime, that I can, you know, so this M1 prime has this structure that M1 prime minus M has this block H1 that we had, and then M2 prime creates the error block H2. Then, you know, then basically I can just consider that, you know, that there is always, you can decompose this M prime, the wrong match, as combination of two other matchings, which, you know, one of them was making the mistake at first block, the other one in the second block, and so on. So I can basically do this partitioning. So the difference in this decomposition, what I wrote for you, so remember I'm interested in this basically inner product of the G and this M prime minus M. Now I can just write it as the combination of the, what would have gotten if I was using the mapping, which was making a mistake in only one of these subblocks, right? You can just decompose it. Therefore, I end up making a mistake, right, in my actually in my alignment, if I end up having that this GM prime minus, actually, sorry, the second prime should not be there. So it's G with M prime minus G and the true match M. If this value ends up being larger than 0, I'm making a mistake, right? So I remember this is what the MLED is doing, right? So this error happens either because, you know, you had a, you basically were exceeding in the part which had the first block or the second block, right? So why is this important? It means that I don't need to worry about like having both of these blocks to analyze. So I can just concentrate on analyzing a single block, and then, you know, this is how I'm gonna do my analysis, right? So if my true matching is M, and then M prime is the false matching, right? So recall that what happens is that every user is at most mapped by this you know, correct matching M once, and at most also once by this M prime, right? So it means that you would basically always just have one blue line in your case, and you could always have one red line, right? So this ends up meaning that, you know, the only mistakes you can make are either path or cycles. I think it's easier to show you in this demographic, right? So these are the all possible mistakes I can get in a single block, right? So in a single block, either I get these cycles, like look at the first one, that's when you flip two pairs of users, or you get these paths like the second one that, you know, you have this mistake that, you know, you're mapping U1 to U2, and then U2 is going to somebody else, or so on. Or, you know, you could be in a setting that, you know, the third one again is a path that you are basically mapping again of this form, right? So your U1 goes to some U2 and so on. And again, if you, so these are all possible mistakes that you have, all of them either paths or cycles. So, and then, you know, we can have different names for them. Like, you know, we've called the first one cycle. We call the second one like a balance path. The other one, we call them dominated because one of the matchings has more edges in it. So if the size of my two databases are the same, then I would never have, of course, this path, right? Because I'm forced to always map everybody to each other through this matching. So then it would be in a case that I only have cycles. But if actually the size of the databases is not the same, then you would also have these errors through the path as I described for you. So to give you some, you know, intuition about the analysis, I'm just going to assume, to make life easy, let's assume that we only had actually cycles, right? So basically the size of the databases were the same. Then if I have a false mapping, right, and then let's say we were considering a setting that I was just making a mistake between two pairs, then I would have this cycle of length 4, which I showed you. And then, you know, the Chernoff bound would exactly be of this form, right? So if I was calculating the Chernoff bound for this error probability event, then you would get that, you know, so you would have this XP of the minus I, and then for the Gaussian case, you would have the exact same thing, except that now here would be with the mutual information, right? So this would be what you end up getting. If I have some cycle of a larger length, and remember these are always like even size cycles, so let's say some cycle of size 2 delta, then you can actually upper bound the Chernoff bound and again get a very similar expression, except that you see that here there's a delta in the expressions as well, right? So, and from now on, I'm just gonna, to make life easier for me, I'm just gonna write I, which depending on the case of the alphabet, it could either be this I circular or it could be the mutual information, right? So remember that the total number of the false mapping that I can actually have here, so this false mapping M prime can induce like cycles of this length to delta, right? Compared to the true mapping, that was what I was showing to you. The maximum of them is this combinatoric quantity, and this is actually upper bounded by this n to the delta over delta. So then if the true map is like, say, like, you know, what you're trying to estimate is estimate of in, this M is this M hat, then the ML estimator is basically, if you're considering what is the error that it would make, the expectation of this error. So I have this many cycles, right? And remember the probability of that event was upper bounded by this XP of this minus delta I over 2, right? So this basically would be my expectation of the error, right? Number of the, you know, the error I get from such cycles, right? So this is what we get. So the way I'm getting this, of course, is through a union bound, right? Because I calculated all such cycles, I upper bounded it by n to the delta over delta, and I'm just basically summing all of them up, right? So clearly this is not the correct value, it's just it's a union bound, right? I'm considering all of this. So of course, you know, in general, a user cannot be in multiple cycles. So this is, of course, loose in general, right? This bound. So, but, you know, nonetheless, like, you know, we can actually use it, right? So I have this value here. Now, remember that if I had a cycle of length 2 delta, like say if I had a cycle of length 4, you were making a mistake for basically 2 users, right? So so that was the mistake you were having. So you have this many errors. So for each of them, so if you just multiply it by the delta, of course, the delta vanishes. So you end up having the error is bounded by this expression on the bottom of the slide. So this is exactly the expected number of the errors that you would get if you had cycles of length this 2 delta, right? So this would be the upper bound on the error. So of course, in a special case, when this is equals to 2, then you don't have an error, right? You're mapping it to the correct person, so let's not worry about that. So the shortest error-inducing cycle then has to be of length 4, as I showed it to you, right? And then I need to then look at the all of my errors. So this was for a specific cycle of length, you know, 2 delta. So I have to look at it for all these cycles. And as I told you, the first one is not an error because you just map someone to itself. So you start from delta equals 2, go all the way to n, and this is an upper bound that you have, right, on your error. So we can see easily that if your basically I is larger than 2 log n plus this little omega of 1, then you're gonna have that, you know, this is actually gonna converge to this expression, and this was exactly what we were having, right? So this was the value of my the value that I had for you earlier in the slide. So I want to go back 1 second to these results and just end it on that. I've just repeated it on this slide. My apologies. So I just want to quickly describe my case here. So recall this was exactly what I had for you, right? The achievability that I was describing for you. It was exactly this expression of the achievability, right? So the way basically we derive this is by through this cycle analysis. So I don't have time, unfortunately, to go further about this. So this union bounds, this basically the value that I was calculating at the end, unfortunately, this is not gonna, this geometric series is not gonna converge if I'm not in this high correlation setting. So when your correlation is lower, that was the regime where, you know, I had this just log n thing and I was describing you the results there. So in that setting, unfortunately, I cannot use the same analysis. The union bound becomes much looser, and then we have to use more complex approaches to actually still handle the errors there. And if you're interested, you know, all the details are in the papers, and I would be happy also to answer questions. So I believe I have to stop now and take questions. If I'm mistaken, please let me know about the time.
Yeah, I think this is it's a good time for questions. So are there any questions? I think there was one question in the chat, Negar. The question was, is this related to the
Yeah, it
Bhattacharya
looks similar because the value of the correlation, yes, it is similar, correct. In fact, in the case of the graphs, it's even more obvious. Yes.
John, did you have a follow-up?
Sorry, I'm muted. Yeah, not really. I just saw the formula and it looked like sum of square roots.
Yeah,
It really rang a bell. Yeah.
Yeah, it's exactly, you're absolutely correct. It's the value of your correlation in some sense, right? So yes.
Okay, thanks.
Yes. So, I mean, I don't know, like, you know, I try to give a little bit like the results and then maybe the intuition behind them. I hope this was okay. I apologize. I realized I had a few typos on the slide, so I would clean them up and maybe give a better version if you need to have the slides on the website. But I hope that the ideas were clear, right? So if, you know, I think it's an interesting problem because it's a very interesting application, and it ends up being fundamentally very similar to many other information theoretic problems that we have looked at, you know, having this basically information theoretic measure that has this achievability and converse. So the problem is hard though. So if you look at what I have plotted for you, in none of these plots I have the exact regime, right? So I know, of course, the true curves are gonna lie somewhere between the green and the red regions, but I don't have the expressions, right? So we just have the order of how the errors are decaying. Any other questions?
I guess I could ask one unrelated. Has anyone made any attempt to start where you have to like do this from data, not from knowing the distribution?
Yeah, so this is a very interesting question. So there is a version of this problem. It's called a shuffled regression. I think it's Martin Wainwright's group has some results on this. So in that problem, you basically have a little bit of a more complex setting that, you know, you basically don't necessarily even know all these distributions, right? So yes, there's some attempts to it. But I mean, so I cannot say which problem is really harder, because in each problem you have some simplifications and the others, like, you know, so like for instance, you might have this notion there in the regression that you assume everything is linear, right? So you have a linear mapping. So in a sense, in some sense it's easier, in some sense it's harder. But yeah, I think ideally what would make sense is try to also learn these, but you can imagine that it's very difficult, right? Because you have to learn this, you have to assume an alignment, then try to learn the distribution, then check, see whether it's correct, right?
Mm-hmm.
Because the distribution is obviously induced by your mapping, right?
Yeah, and I do remember that seeing the shuffled one a while ago, and now that you mentioned it, I see some similarity. Yeah,
it is actually related. I don't think people recognize that it's the same problem, but it is the same problem.
Yeah, I realized after you mentioned it. Yeah.
Yeah, so there's a bunch of, in fact, at some point, if I'm less lazy, I should write a tutorial. I don't know if I can see you guys. Let me make sure I see people when I talk to you. So Yeah, so when I'm less lazy, I think I should try to write a tutorial because I think it's very helpful. There's many problems that people are looking at, and you know, like this graph matching problem that I have worked on myself. Then there's this also, like, you know, people look at some of these partial graph embeddings and so on, and they're also related to the same problem. So people in statistical physics are very interested in this. Also, there's been some really nice work by Yihong Wu and Jiaming Xu. And I mean, all of the problems are related, and I mean, I'm sure they're aware of it too, but you know, it would be nice to, like, you know, have some perhaps paper that tells how all these results are related to each other. So there are different versions of doing similar things, by the way. So also in computer vision, in statistics, people are again very interested in these alignment problems as well. So there are versions of this that people look at these just as a, you know, quadratic assignment problem. You can see that, you know, you're trying to find these matchings, and there's also results in that space.
Okay, thanks.
Negar,
Yes.
Negar, is that somehow connected to the double-sided information bottleneck, which is used, you know, in hidden variables, also in the graph things that you've made, graph matching problems, and also, you know, those are different problems if you try to optimize correlation of mutual information over the double side then. Of the double side thing, double-sided information bottleneck, not just the simple information.
Yes, so I'm sure there is there should be some relationship. To be honest, I mean, I know that, you know, basic information bottleneck because it comes very much in feature selection, right? So I don't know this double-sided basically information bottleneck, but I would love to read about it and see if it's related. So possibly there is a relationship. I mean, I just don't know the literature.
Okay, hopefully we'll discuss that on summer.
Yeah, I would love to learn about it. Yes. But I'm not surprised that it would be related, right? Because, you know, fundamentally.
Yeah, me neither. I wouldn't be surprised either.
Because, you know, this is really like, these are basically capturing correlations among features, right? So all these problems that have notion of, So you're just
looking forward to your tutorial on to the overview.
I always make these promises and I never deliver, right? But I think at some point I think it's really would be great because, you know, I think biggest service I always feel that one does in academia is through teaching and, you know, tutorials, because I'm of the belief that there's so many smarter people out there that if you just tell them the problem, they end up doing something much better than what I ever would achieve. So it's very helpful to make sure it's communicated. Any other questions?
Actually, Negar, you mentioned graph alignment a couple of times. So yeah, I mean, I think that's an older problem than this, right? So is like, so you mentioned the connection a few times, but are these two essentially the same problem, or
they have lots of similarities? So let me just go on the earlier slide. Very, very good question. So you're absolutely correct. Just want to 1 second remind you what does, I mean, of course you guys know, but for the students, I want to make sure they know what we mean when we discuss this. I remember, where was I doing the graph? Okay, so the difference is in the graph alignment, and you're correct, it's a much older problem. It actually goes all the way, as far as I know, the oldest version of it goes to Erdos, right? Because there it's related to this notion of graph isomorphism. So you have two identical graphs, and then the question is, can you use the topology of the graph to map the vertices? So the version of the problem that I got interested in working is this so-called noisy isomorphism. So the two graphs are not exactly the same, but there is correlation between them. So, you know, so if you have an edge in one of them, it tells you something about the likelihood of presence of edge in the other graph. So you have these correlated graph models. And actually the paper that got me interested in this is by Pedrosani and Grossglauser, and they derive the information theoretic region for this, except that between their converse and achievability, I think, actually I don't remember if they had a converse, but definitely the achievability was a bit loose, because there's a converse that indeed translates again from classical results. You just, at least for Erdos-Schreini, there is a point that when the degree of the graphs is lower than a certain amount, this log n over n, you get isolated vertices, and there's no way you can match isolated vertices, right? Because you have to use the topology. So then what we did is that we tightened that threshold, and we show that it's log n over n is the exact information theoretic threshold. But absolutely correct, that's an older problem in its non-noisy setting, and the noisy one got a lot of attention in recent years, and the application is both, it's interesting because it's something that arises in matching of protein network, but also again in vision. So when you're trying to do this alignment of the motions and so on, so it has a natural application, and the things are noisy. So in the graph setting, you are using, so what is basically depicted here, you're using the connections between these vertices to do the analysis. And you can see that this actually makes it a bit harder, right? Because you don't have any more this IID-ness across the users that I have in the database setting, because it's not that you're just looking across the graphs, but between the vertices in a graph, you have a correlation as well, because it depends who you're connected to. Hence, you need to look at basically this lifting of the objects too. You care about the edges, you look at pairs of vertices, and it's in a sense harder. And we don't even dare have efficient algorithms. So, so you don't have any of these type of polynomial time algorithms that exist in the database setting. So lots of the work in the graph matching, after we got the threshold, at least for this class of, for Erdos-Schreini graphs and so on, people still don't know, what is the limit for having basically polynomial time or efficient algorithms. So for some regions of high correlation, we have nice algorithms, like we even have one ourselves, right? So it's a polynomial time algorithm we have that is some generalization of Erdős's work. But and then again, Yi Hong has some very nice results on this, Jiaming Wu, Boaz Barak from Harvard, and I think Elkanon Mosul from MIT. So people have some also algorithmic results in this space, but many of it is still open. And then there of course remains hypergraphs. But if you have more than 2 graphs, you have multiple of them, then how do you do it? There's tons of things that stays open. And it's very nice because I think these are fundamentally information theoretic problems. Yeah,
thank you, Negar. Do you think that so the IID assumption plays a big role in your work, right? So yes. If you look at the interactions between users, do you think that has a role in the database alignment problem? Because you can imagine in medical records, right? You can imagine that the subpopulations of users who are definitely correlated, right? So absolutely. Or you can think about, let's say, your family members, right? So then you would obviously have correlations among the users. So, or let's say there are conditions that if you're from even same zip code, let's say there's some pollutant, right, that is impacting, absolutely, and genetic mutations in certain subpopulations. So yes, the reason we did not consider that is not because it's not exciting. Actually, that is the more exciting version of the problem. It's just was so hard for us even doing this. Yeah, even the IID case is hard, right? It's, if you look at I'm really shoving things under the carpet to give the intuition, because I thought, just to give you an intuition, how is this problem analyzed? You read the paper, you would see that honestly finding even this Chernoff bounds and just doing the calculations is quite difficult. And some of the bounds, to clean them up, my student Osman in this space did it, and my former student Daniel in graph alignment problem. I think I would have gotten stuck in the combinatorial part. I think they're really brilliant that they managed to actually get clean expressions. So it's tough, but yes, absolutely. So I think the right way would be to eventually also consider correlations. Yeah. So are there any other questions for Professor Kiyavash from any of the students?
Actually, I have a question. Hey, sorry. Just curious. So you look at the case whereby you allow a fraction of the database to be unmatched, matched incorrectly. No, a vanishing fraction. Do you actually did anybody consider just a positive fraction to be correctly matched?
So we have not looked at this for databases, but
Uh-huh.
we actually look at this partial alignment in some settings for graphs. So
I
we
see.
have this paper on this so-called K-core alignment that looked at it. But yes, that is also interesting, you know. So there's all of these problems in some sense also have a, you know, to me, like it's a bit like full decoding, right? Or partial decoding. And you can think about there is also a more signal processing hypothesis testing version of the problem as well, right? That in a sense, I discussed that a little bit when I talked about the threshold setting, that you just want to be two user. But, you know, one could think about all of these problems would have also a hypothesis testing version, right? That you might want to do it between either subset of users or just set of users.
I see.
So, I thought you were actually going to ask about because your right now your work the fraction of errors vanishes. Did you consider the case where it doesn't vanish, where it's like I don't know, you know?
Yeah, I mean, just require half of it. Correct.
Yeah. I mean, so there's
exactly. I think
that's what the question. Yeah,
right. That's exactly the question. I think that if I'm
not
mistaken,
yeah.
So it's called a K-core, is it? K-core.
Yeah, so you can look at this K-core alignment, right? That's
Interesting.
just for the graphs, right? So,
which
is, if you look at this partial recovery and, you know, there's this notion of something we described. You don't do MLE, you do something called K-core alignment.
So is this efficient or because to look for, I don't.
So in general, these problems are not efficient, right?
Okay, sure.
We're happy to analyze them, especially in the graph case.
I see.
So I have only one paper that looks at efficient algorithms, right? Which is polynomial time. But even there, let's be careful, right?
Polynomial time.
Exactly. You know,
yeah.
In a CS theory sense, but think you're doing it for millions of users on a social network, right? Having an algorithm which is polynomial time, right, with like n to the 6 is not efficient either, right? So
indeed, yeah. Especially when you look at DNA. Yeah.
Exactly.
Yeah.
So I think we really have looked at it much more information theoretically and also from CS theory way, but this is not in a sense, you know, like I'm sure if you talk to really practitioners, they would say like, what do you mean this is efficient?
Indeed. Okay.
So is partial alignment have errors? I thought for that you're trying to just get. Yeah, I mean, so is the question I asked the same as K-core? Like so I'm saying you want to get the whole, like the full alignment, but you allow errors. Is that the same as what you said?
No, it's not exactly the same, but it could give you, right? So I'm saying that you do partial alignments, right, that can result in calculating then allowing a certain number of errors, but it's not exactly the same. Yes, I was just saying that we have that result, but it's not been, we have not done it yet.
Okay, cool.
Yeah.
Okay, great. Any other questions from anybody?
So yeah, one more question here is all the alignment and maximum likelihood estimation is between two databases, right? Database A and database B. In practice, I think is there a need to analyze the alignment of more than two databases, and then the problem will become much more complicated, right?
You are absolutely correct, right? So for instance, in the graph problem where I started from, so there is example. So I was on a thesis of a student at EPFL, in fact, and that's how I kind of, you know, got also interested a lot about this, you know, I mean, before that too, but also then I got even more interested in this multi-graph matching in some sense. You're correct. So in things like, say, among species, you might have some notion of aligning protein networks and so on. And they really naturally, the problem is not between two graphs. It just becomes much harder. So there is, surprisingly, there's really nice algorithmic work in computational biology, but there is not a very good analysis for it. So so the problem gets much harder if you're looking for multi-databases or multi-graphs. Yes, but it's definitely an open problem. Yes.
Okay, so yeah, the computational capacity will go significantly, and also maybe the error analysis, right? The bound analysis will also become
for us, honestly, we didn't even think about computational complexity. You're absolutely right about that, but we even have a hard time analyzing the problem, right? It just gets so much harder because you can now imagine, right? So I was looking at errors across only databases. Still, you get all these paths or you get cycles you have to analyze. If you have more of these things, so the dimension goes higher, then you get these more complex also objects you have to analyze.
Yeah, it's very interesting problem. Yeah, very interesting related to graph theory, signal processing, and information theory. Yeah, really
exactly.
interesting.
It's really beautiful,
Yeah.
And I think there is so much space to work here. So all the way from algorithmics to information theoretic side. So I hope that other people would be interested in it too.
Okay. Yeah. Yes. Thank you very much for the sharing. Yeah.
Thank you so much.
Okay.
Okay, so I think let's thank Negar again for an excellent talk and an introduction to the data alignment problem. You can all, if you go to Zoom, there's some reactions. You can have a reaction.
Yeah.
Okay, so thank you again, Negar, for your talk.
Thank you all very much for attending the talk, and it was really lovely to see you, Mehul, Shalomo, and everyone. Even if it was virtual. So I hope to see you all soon, and maybe you can come visit me.
Absolutely.
See you, Negar. See you.
See you. Bye.
Have a great one. Bye bye.
Thanks.